Like all forms of media, I sometimes have to issue a retraction. And I have to issue one now because in the previous video, I went ahead and calculated the pH of phosphoric acid. And I just went ahead and said, oh, you get 2 hydrogens. Well, I was a little mistaken. While that is partially true, it is not completely true. Because the pH of a polyprotic acid, an acid that can donate more than 1 hydrogen, is not driven simply by stoichiometry. Even if it's strong, it will dissociate in steps. Meaning first, phosphoric acid will lose 1 hydrogen and become the biphosphate ion. And then that biphosphate ion will lose another hydrogen to become sulfate. So if you look in your notes, you'll see that phosphoric acid will lose 1 hydrogen at a time, first becoming bisulfate, lose another hydrogen, and become hydrogen sulfate, or phosphate, sorry. But each time, the Ka value gets lower and lower because it takes more and more energy for water to get in there to pull that hydrogen off because the phosphate is becoming more and more negative. So from a positive-negative stance, an electrostatic stance, that hydrogen does not want to leave as the phosphate, as the overall molecule becomes more and more negatively charged. However, the first dissociation is the greatest. All other dissociations will decrease, as you can see. In fact, because that first dissociation is so great, it's so great for all polyprotic acids. Let's look at a couple. It is actually the first dissociation that is most useful when determining the pH of a polyprotic acid. And because these second and third dissociations are so infinitesimally small when compared to the first dissociation, the concentration of hydrogen you receive from them can be ignored. Much like we ignored or neglected X, we can neglect the second and third dissociation and say each acid can only donate 1 hydrogen, unless it's a strong acid. So in the case of sulfuric acid. In the case of sulfuric acid, it really becomes dependent upon what the overall concentration is. If you have something that's concentrated, like 1 molar sulfuric acid, that 1 molar sulfuric acid is not going to change a great deal based on a Ka value. If we look at the first and second dissociation Ka values of sulfuric acid, the first dissociation, Ka1, is large, and therefore the sulfuric acid is going to break down into hydrogen ions and bisulfate ions, meaning we're going to get that 1 hydrogen off rather easily. However, the second dissociation, the Ka2, is small in comparison to 1 molar, and therefore can be ignored. So really, it's this first dissociation that's all that's going to matter. So for sulfuric acid, we're going to end up with 1 hydrogen. I'll go ahead and show that now actually on a rice table. So we know that the concentration of hydrogen ions is 1 mole. We know that pH is negative log of that, so negative log of 1 is 0. Our answer has 2 sig figs, so our problem has 2 sig figs, so our answer has to have 2 decimal places. Again, this is because this is concentrated sulfuric acid. The stronger, since this is concentrated sulfuric acid, the greater dissociation, being the first one, is going to be the only thing we factor in when we calculate the pH. However, if it's not concentrated, in its first dissociation, sulfuric acid is going to lose 1 hydrogen and become sulfuric acid and the bisulfate ion. And we can determine the concentration of hydrogens and bisulfate you would get simply because this is a large Ka. It means it's going to go all the way to completion. Notice that there is only a single arrow here. And this is going to go all the way. So if I filled this in my rice table, it would look like this, where all of my hydrogen and all of my sulfate, all of my hydrogen sulfate, sulfuric acid is used up, giving me 0.1 molar hydrogen and 0.1 molar hydrogen sulfate. In its second dissociation, the bisulfate ion is not as willing to give up another hydrogen, and therefore our Ka value is significantly less. Also, if we look, our concentration of the bisulfate ion is rather small, or rather dilute compared to this Ka value. So we aren't going to be able to ignore X like we normally would. So that means we have a quadratic problem or a quadratic formula in our future. If we fill out the rice table for this, we have to take in consideration the concentrations of both the hydrogen ions already in solution, it's like a common ion effect, and the bisulfate. So if I plug those values in, I'll get something that looks like this, where as this bisulfate dissociates, we end up with X amount of hydrogens being added to the 0.1 we already have, and, well, no one's really going to care about the sulfate ion. You can hopefully remember that Ka equals the concentration of hydrogen times the concentration of sulfate divided by the concentration of bisulfate. So if I set this up, Ka equals 1.2 times 10 to the minus 2, and that equals 0.01 plus X, that's for the hydrogen, times the sulfate, which is X, divided by the hydrogen sulfate, 0.01 minus X. Distribute, and we get this. Cross multiply, and we're going to find that we end up with, but before we do that, whew, what a mess. Alright, combine like terms, get everything on the same side. I'm going to save some time and just do it. If you'd like, you can pause it and see if you can do it yourself. There we go. Oh, fix that. And once we put this into our quadratic problem, we find that the concentration of hydrogen, or X in this case, is 0.045. Now if we take the concentration of hydrogen from the second dissociation and add it to the concentration of hydrogen from the first dissociation, because really this is all happening at the same time, we find that the concentration of overall of hydrogen in this reaction, drum roll please, is 0.0145. And yes, if you were paying attention, I copied it wrong from my notes. The second concentration of hydrogen is 0.0045. I truncated a zero on accident. So if I know the concentration of hydrogen, it's a simple matter to say the pH equals the negative log of the concentration of hydrogen, and therefore our pH is 1.84. Two significant figures in our problem, so our answer has to have 2 decimal places.